Okay. Good morning, everyone. I hope you all are having a wonderful event so far. I'm Pratik Devkota, a computer engineer and a machine learning engineer. I recently graduated from the University of North Carolina at Greensboro with a master's degree in computer science. Today, I bring to you this presentation on my paper using ontology embeddings with deep learning architectures to improve the prediction of ontology concepts from literature. This collaborative work features me and my supervisors and co-authors, Dr. Soumya Mohanty and Prashanti Manda. Now, without further ado, let's get started. Today, I'll go through the following points, starting with different ways to automate ontology embeddings. I'll then discuss the use of deep learning algorithms for named entity recognition and ontology embeddings. Later, I'll describe how we have augmented the contextual information from scientific literatures with the semantic relationship that exists in ontologies. And finally, I'll present the results of our research, followed by further analysis. We've been working on the automation of ontology annotations for the past couple of years, and here are some of our recent works related to that. Excuse me. In this paper, we augmented the information from human curated ontology annotation dataset with data from other sources like BioThesaurus and UMLS. There we trained deep learning models on such augmented information, and we were able to see improvements in performance. And in the last two papers, we developed deep learning models that would not only use scientific literatures as input, but also would consume additional information about the semantic relationship that exists in gene ontology. In this paper, we used Jaccard semantic similarity between ontology concepts and added that information to train deep learning models. And in the last paper, we introduced boosting as a post-processing step where we would boost the confidence of prediction of ontology concepts based on their confidence of association with the parent concepts. This paper is another attempt to incorporate the semantic relationship between different ontologies and different concepts in an ontology into the training of deep learning models. Here we are letting the model learn not only from the context that's present in the scientific text, but also from the association between concepts in the entire gene ontology. Our focus here is on gene ontology, but this approach is applicable to other ontologies as well. Now, talking about the overall approach, our implementation is a two-step process, where the first step is to compute embeddings for all concepts in gene ontology, and then the next step is to provide these embeddings as input to deep learning models, along with the human curated annotation dataset. Now, the first step, computing embeddings for Go concepts. But what are embeddings? Basically, embedding is the concept of representing text or words as vector of numbers, such that when they are placed in some n-dimensional embedding space, the semantically similar words, they lie close to each other. Simply put, embeddings capture the association between different words. For example, in this figure, we can use embeddings to deduce that there is some relationship or association from king to queen, and it is similar to the association from a man to woman. As another example, relationship from walking to walked is semantically similar to that from swimming to swam. These semantics or association or relationships are learned from context that they appear in. Here are some of those examples. There's a married relationship between man and woman, and the same relationship exists between a king and a queen. There may be a birth relationship between parents and a baby boy. And by providing such context, such examples to a deep learning model, we can extract the embedding vectors. But how do we apply that to the gene ontology? As we all know, the ontology is a directed graph with the relationship between different concepts, but there doesn't exist any context that describes the association. So to generate such context, we use node-to-vec algorithm, a popular algorithm that was introduced in 2016. First, we use a method called random walk with these parameters that we can tune. The walk length defines how many nodes we want to explore. A walk number defines the number of samples that we want to generate. And P and Q are probabilities that control how we want to explore the nodes to generate context. A lower value of P and a higher value of Q essentially keeps the walk close or local to the source node. In our case, since we wanted the context to be more focused towards the immediate parents of a source node, we chose the value of 0.5 for P and 2 for Q. Also, we set the walk length to 5 and walk number to 100. And after random walk, we will get context like this. In this case, I have kept walk length and walk number fairly simpler for demonstration purpose. But with this method, we will get context like the one listed here. Then we used an algorithm called word2vec to generate the embeddings. Now that we have the context, I won't go into much detail about word2vec here, but we trained a model with a batch size of 50 for 3 epochs to generate 120-dimensional embeddings for all the gene ontology concept that exists. And now that we have generated the embeddings for all the gene ontology concepts, we train deep learning models utilizing these embeddings. To train our deep neural network, we used a Craft dataset for both training and validation. Craft includes 97 articles published in PubMed and their annotations from ontology experts. At this point, Craft is pretty much a gold standard for named entity recognition. It has almost 30,000 sentences or 30,000 inputs that we can train a model on. And to train a supervised deep learning model, we must provide fixed length input and output sequences. So for input, each article is divided into sentences, which in turn is further divided into words called tokens. As an example, here's a sentence, and here are its corresponding tokens. Now for each token, we must specify whether it's a concept or not. So if this is a sentence and it's broken down into tokens as such, here the highlighted tokens are represented by some gene ontology concepts, and therefore they are mapped to certain Go IDs. All tokens that represent a concept are mapped to their corresponding Go IDs, and tokens that do not represent any concept are mapped to an O or out of concept class. These inputs are then fed to deep neural network, where it goes through different layers, focusing on different contexts or properties of the text. It eventually outputs a vector of numbers like this. Here, a vector is different from the one that we discussed earlier for embeddings. In this case, the output vector represents a probability distribution for each token. And from this distribution, we extract the concept with highest probability and assign a Go concept to that token. Initially, all of these vectors are all random, and they do not accurately represent the correct output. But with more input data or more input tokens for training, the model starts to understand the language better and capture necessary information and relationship, and slowly converges to a state where there is low error between what it predicts versus what it's supposed to predict. Eventually, it completes the training, and we get the output as vectors with probability distribution, which are then mapped to some Go terms or Go concepts. Now let's talk about our implementation in detail. Here's an architecture of one of the deep learning model that we would like to call it a baseline model. It has the following inputs. The first one is the tokens. The list of tokens are fed into the model as such. Then we have character level inputs, where each token is further divided as a sequence of characters. Finally, we have parts of speech as another input pipeline. These inputs pass through embedding layers. The embedding layers are used to map the input to dense vector in continuous vector space. These layers are fairly simpler, and they can only retain some level of semantic meaning. You may have noticed that we have used separate embedding layers for words, characters, and parts of speech, since they all have their own syntactic structure and semantic nuances. Additionally, we have used a bidirectional GRU layer just for character level input. This is proven to be useful in capturing morphological information such as prefixes and suffixes, especially in scientific text where prefixes and suffixes can largely vary the meaning of a word. Now, all of these intermediate outputs are concatenated and passed through a dropout layer. Here, the dropout layer is used to avoid overfitting or to help the model stay more generalizable. Now the bidirectional layer here are used for useful in capturing the contextual information from the entire sequence, meaning that this bidirectional layer allows to learn context uh, not only by looking at the words that comes before a particular token, but also considering the whole sentence as whole sequence as in general. A word can have different meaning in different sentences, and therefore such words depend on the context that they appear. These bidirectional layers are useful in understanding those uh, context and the language overall. Now we have the dense layer, which is used to combine all of the features that we have learned from previous layers. And finally, we have the output layer that outputs the probability distribution of each token. And then a concept with highest probability becomes our output token. Of course, for the model to learn, the final output is to be compared to what it's supposed to predict, which we call the ground truth. And then some loss is then calculated. The loss is then back propagated to adjust all of the intermediate parameters that were set during the forward propagation. This entire process happens for multiple iterations before they finally converge. And in this model, since we are only predicting Go annotations or tags, we are calling it tag-only baseline architecture. This is another architecture which looks like similar to the tag-only architecture, with the only difference lying in the final output. Here, the output is the embedding that is learned in the first step, that was learned in our first step using the entire gene ontology hierarchy. The predicted embeddings are 128-dimensional vector of real numbers, unlike tag predictions, which was again the probability distribution. And we'll have our embedding output as such. And since it outputs embedding, we are calling it embedding only baseline architecture. This is where things get a little interesting. This is a cross-connected architecture where everything is same till the final bidirectional layer. But here, this section is where there's a difference. Now, the output of the bidirectional layer is further concatenated with the output of the tags to predict embeddings. The whole idea here is that we will let the model first learn the context of the scientific literature till the tag output. And then because we are also instructing the model to predict their embeddings, the model should start to make some adjustment to previously learned parameters to capture the newly introduced hierarchical relationship between different concepts as they were learned from the entire ontology hierarchy. Basically, we're teaching the model to understand the context of scientific texts and their associations with some gene ontology concept, while also making the model aware of the hierarchy that exists in gene ontology. And since we have two different outputs, here's an example of what the tag output looks like and what the embedding output looks like. And since we have the output of tag fed to the embedding, we would like to call it tag to embedding architecture. Now, to evaluate the model's performance, we have used precision and recall, which are the traditional or general evaluation metrics used. More importantly, we focus on F1 score here instead of accuracy. There is always an imbalance between the number of concept annotation and out of concept annotation that's present in scientific literatures, where we have far less number of words that are associated to some concept than words that do not have any association with ontology concept. Therefore, F1 here gives a better representation of the model's performance in terms of prediction. We also focus on Jaccard semantic similarity here. It measures the ontological distance between two concepts. It is important to access partial semantic similarity here. So in cases where a model is not able to correctly predict a concept, we're trying to evaluate if the model is able to predict maybe a semantically similar concept. Now, this is how our model performed with different architectures. Since there are two outputs involved, we have calculated F1 and semantic similarity score for both ontology embedding prediction and tag prediction. And we can clearly observe from the table that an addition of ontology embeddings have always improved the model performance over the baseline architectures in terms of tag F1 score and tag semantic similarity score. Moreover, we can also see that the cross connection of output gave the best result when the output of tag was fed as input to embedding output layer. Let's discuss the result a little more. For the baseline tag-only architecture, the tag prediction had good accuracy, but had limited predictability. What do I mean by limited predictability? Well, in this case, the corpus has annotations for the corpus of the training data set that we have used as annotation for about 1,000 unique gene ontology concepts. However, the gene ontology concept itself has over 45,000 different annotations. So since the model only saw 1,000 concepts during training, for any on-scene token, it can only suggest a concept from those 1,000 scene concepts. Furthermore, this model is not aware of the semantic relationship that exists in the ontology hierarchy. Now with baseline embedding only architecture, the model was able to suggest the concepts that were outside the corpus, that were outside the training corpus, but the model has relatively low scores. With cross-connection architecture, the model can predict the concepts within the corpus with much more confidence, while also showing significant improvement in the performance in terms of ontology embedding prediction. We can observe from the result here that we saw 23% improvement in ontological embedding F1 score and 9.4% improvement in ontology embedding semantic similarity score, while we also saw improvements in tag F1 and tag semantic similarity scores. Now, for the future works, with a rapidly growing community of generative AI and open source large language models, our future work would be directed towards making use of these models, as we believe that they can understand the context of biological literature text even better. On top of that, we can train the model to build a better understanding of the structure and components of ontologies without having to implicitly specify the hierarchy. This work is funded by a career grant to Dr. Prashanthi Menda from the Division of Biological Infrastructure at the National Science Foundation. I would like to thank my supervisors, Dr. Soumya Mohanty and Dr. Prashanthi Menda, for all their help and support in this research. Now, thank you guys for tuning in, and I apologize for not being there to present this in person. But if you want to learn more about the research or if you have any feedback, please feel free to reach out at that email, or you can also use the QR code here.